Hello, my name is Bill Robbins. In this video I'm going to talk about snubber circuits that are used to protect semiconductor power devices. More specifically, I'm going to talk about the following topics. First, an overview of why we need snubber circuits. Then I'll talk about first diode snubbers, and then turn-off snubbers, overvoltage snubbers, and turn-on snubbers. I'm not going to go into detail on Thyristor snubbers because they are essentially the same as diode snubbers, but I've included some details in the lecture notes for those who may be interested in that topic. Going to the next slide. Why do we need snubber circuits? Snubber circuits I'm talking about are used for hard switch converters, and their main function is to protect the semiconductor device. We can protect the device first by limiting the device voltages during turn-off transients, limiting the device currents during the turn-on transients, limiting the rate of rise of currents through the device during turn-on, limiting the rate of rise of the voltage during turn-off, and in general, shaping the switching trajectory of the device as it turns on and off in order to minimize the power dissipation. There are three types of snubber circuits. There are unpolarized snubber circuits, which are used to protect diodes. There are polarized RC snubbers, which are used as turn-off snubbers and also as overvoltage snubbers and to limit the rate of rise of the voltage. By polarized, I mean in addition to the RC elements that make up the snubber, there's also a diode. We also use polarized RL snubbers, inductor resistor snubbers that are polarized, in order to have a turn-on snubber and also to limit the DIDT during device turn-on. The first snubber I'm going to talk about is the diode snubber. The need for the diode snubber is shown in this circuit. The actual snubber itself is the RSCS element that or circuit fragment that I'm circling here. If we don't, the reason that we need snubbers is because of the stray inductance that the circuit may have. If we look at the current waveform in the diode as it turns off, as we're aware, it ramps from its on-state voltage negatively down to a peak reverse recovery current, termed I sub RR, and then the current decays down to zero. During the ramp down, the rate of fall of the current, dIdt, is governed by the inductor, and the rate at which the current can fall is V sub d over the value of the inductance. At the time we reach the peak reverse recovery current, the diode voltage then can change from its forward bias value very quickly to a large reverse bias value. And the magnitude of that reverse voltage is dependent on the dIdt value and on the stray inductance. If we assume the worst case, which is the diode turns off instantaneously at the peak reverse recovery current, that is a snappiness factor of equal to 0, then we're going to get the largest dIdt. Fortunately, because of the presence of the snubber, we don't have to interrupt that current instantaneously because of this alternate conduction path, and so we are limiting the peak over voltage. And that peak over voltage I'm showing here is V sub d plus L times dIdt. And the problem arises is if this voltage is larger than the breakdown voltage, the diode could go into avalanche breakdown and destroy itself. So to analyze how the snubber functions, I'm first going to analyze a simpler version in which we model the diode and the snubber and the inductor in this relatively simple circuit where the switch opens at diode snap-off, that is, at the peak reverse recovery current. And here I'm assuming then that the diode snaps off instantaneously. In this arrangement, if I assume that the snubber resistor is 0, I have then a series RC circuit, shown here in the upper right-hand corner, and I can derive the equation for the capacitor voltage as a function of time. That is the equation here which I am referring to, and the boundary conditions for this are the capacitor voltage is 0 at t is equal to 0 at the instant of snap-off, and the current Flowing through the capacitor is the inductor current at t is equal to 0, which is the reverse recovery current. We can easily solve for what the capacitor voltage as a function of time is, and that's what I've indicated here. The parameters in this equation, first of all, omega naught is, as you would expect, 1 over the square root of LC. The normalizing capacitance C base is equal to the stray inductance times the reverse recovery current squared divided by the power supply voltage squared. The peak voltage is given by the next equation. And I have plotted here the normalized voltage, the actual voltage divided by V sub D as a function of the normalized capacitance, CS over C base. Initially, we have a fairly rapid decrease in the overvoltage as we increase the capacitance C sub S, but by the time we reach, for example, CS equal to C base, we've reduced the overvoltage down to a normalized value of about 2.4. Further increases in the capacitance value above C base are not going to reduce the voltage by very much, and so often we use the capacitor set equal to C base as our design criteria for sizing the capacitor. We can reduce the voltage even more by adding a finite snubber resistance. In that case, we have an RLC circuit that I'm showing here. The governing equation is derived here for the inductor current. The boundary conditions are nearly the same. The current flowing at t is equal to 0 is the reverse recovery current. The rate of change of current at t is equal to 0 is V sub D minus IRR times RS over the stray inductance. With a considerable amount of algebra, one can derive the voltage across the diode as a function of time. In order to put it in this relatively compact form, it's necessary to define a series of intermediate variables. Omega A is omega naught times the square root of 1 minus alpha over omega naught, the quantity squared. Alpha is the so-called damping coefficient, Rs over 2L sigma. Omega naught is the same as we've defined earlier. The phase angle phi is given by this term, and I forgot to have a bracket here on the right-hand side. Eta is the normalized capacitance. That's this parameter right here. X is the normalized resistance, Rs over R base. R base is V sub D over IRR. C base is the same quantity that we defined earlier. It's equal to L sigma times IRR squared divided by V sub D squared. And then finally the parameter xi is the inverse tangent of alpha over omega A. Again, with some more tedious algebra, one can derive that the maximum voltage occurs at a time t sub m. T sub m is given by the equation that I'm indicating here. At that time, the normalized maximum voltage is given by the expression that I've written here, and it involves the terms eta and x and the time t sub m and alpha as well. Again, I have put in again on this slide the definitions of these intermediate variables. I have plotted the normalized voltage as a function of Rs over R base, assuming that we are using the optimum value of resistance of about 1.3. And the minimum occurs at, whoops, I'm going too far here. I got to get back to my slide. Occurs at Rs is equal to 1.3 times R base, as I've indicated. That minimum is right in this area right here. I can even go a little bit farther and come up with a design nomogram for the diode snubber. Here I have plotted in red V max over V sub D as when Rs is equal to the optimum value. The optimum value of resistance varies according to what CS over C base ratio is, and that's this blue curve that I'm showing here. If we choose CS equal to C base, then we are located on our maximum value of resistance is about 1.3 times our base. And if we go to a value of twice the base capacitance, then RS over our base is about 1.2. So I think you can see that for general purpose applications, we're going to use as a design criteria CS equal to C base and RS about 1.3 times R base. I've also plotted on here a couple of other quantities. The energy dissipated in the resistor as a function of the energy stored on the capacitor at T is equal to 0, that is 1/2 LIRR squared. I've also plotted the total power dissipated in the snubber and the switch, the diode, as normalized to, again, the energy stored in the inductor at T is equal to 0. And clearly, as we keep increasing the value of the capacitor, we're dissipating more and more energy in both the resistor and in the switch. And that is why we typically want to operate in this range right here, where we get the maximum decrease in the overvoltage without going too far and causing too much power dissipation in the snubber resistor and in the switch. The next kind of snubber that I want to talk about is for control switches, that is MOSFETs, IGBTs, field control thyristors, and all of the other devices that are three-terminal devices, namely 2 output terminals and a input control terminal. I'm going to have my discussion in terms of a simple step-down converter where I have stray inductance perhaps scattered through several different places in the equivalent circuit. If we look at the waveforms for the current through the switch and the voltage across it as a function of time, during turn off, the switch current decreases and begins to decrease after the voltage across the switch reaches its value V sub dd. We have a over voltage on the switch because of the stray inductance. And then when we turn the switch on again, the voltage across the switch immediately decreases by L di dt, and that is going to be useful because it causes the power dissipation during turn on to be reduced. However, we have an overcurrent because of the reverse recovery of the diode. And what that means is, if we trace out on the output characteristics of the device, if we start in turn off and turn it on, we follow the trajectory that I have coming up here. We have an overcurrent, and then we finally get to the on state. When we turn it off, we proceed along the path I've indicated here. We have an overvoltage, and we ultimately get back down to the power supply voltage. In both turn on and turn off, if we have too much stray inductance and too much reverse recovery current, both of these excursions take us outside the safe operating area, and that may then damage or even cause device failure. Hence, we need snubbers to control some of these factors, depending on which ones are the most severe. The first one I'm going to talk about is a turn-off snubber for the controlled switch. Here is my model for the step-down converter. I'm going to idealize the switch as nearly being a perfect switch. I'm not going to specialize it to any particular semiconductor device. Freewheeling diode, load current, and this is the turn-off snubber, composed of the diode DS, resistance RS, and capacitor C sub S. The equivalent circuit during switch turn-off is shown below. We have a switch current which is decreasing linearly as a function of time, and that is the equation that I've written here. I'm going to assume that there is no stray inductance, and I'm further going to assume that the switch current is not affected by the presence of the snubber circuit. Under those conditions, we can easily derive what the capacitor voltage and current are during the current fall time. Capacitor current is increasing linearly as a function of time. The capacitor voltage is decreasing according to the square of the time during the time interval 0 to TFI. I'm going to use a normalizing capacitance value of CS1, and we get that value by saying that at the time TFI, the capacitor voltage is at the power supply voltage, and so that gives us a capacitor value of I0 TFI over 2V sub D. Below here I'm showing three separate conditions for varying values of capacitance. If CS is equal to less than CS1, which I'm indicating down here, our waveforms look something like the following. The capacitor current, or the switch current I should say, decreases linearly in time over the interval TFI. The diode voltage remains fixed until the capacitor current has reached I0. It then decreases abruptly to 0. The diode current then comes to the intermediate value that I'm indicating here, and then for the rest of the TFI interval increases until it reaches the value I0. The capacitor voltage is built up fairly quickly, and when it reaches the value V sub D, that's when the capacitor current goes back down to 0 and the diode current then jumps abruptly. If CS is equal to CS1, then at the end of the current fall time interval, the voltage across the capacitor has just reached V sub D, as I've indicated here, and thus the diode current immediately jumps from 0 up to the value I0. If we have a larger value of capacitor than the CS1, it takes longer for the voltage across the capacitor to build up to the value V sub D, and so the the diode voltage building up here, the current through the switch builds up to a value I0 and remains at that value until the delayed value of the voltage across the capacitor reaches V sub D, at which time then the diode can accept the capacitor current and jumps up then to the value I0. Notice that in this situation we are at a position where we are delaying the length of the turn-off transient, and thus we're going to have excessive power dissipation. In order to design a proper snubber for the turn-off, we have to worry about what happens when we turn the switch back on. The reason we have to worry about that is shown, I think, quite clearly here on the left-hand side. Here we have our switch, which has been off for a time. The capacitor voltage is at V sub D. All of the load currents going through the diode. So the diode is essentially short, and thus V sub D is applied directly across the capacitor. If we did not have this snubber resistor, it was just a short circuit, all of that stored energy would be dumped into the switch, causing excessive power dissipation. The result would be the following. The voltage across the switch would build up to V sub D, and the current would build up to the value I0, and then it would keep going because of the extra energy stored in the capacitor, as well as the reverse recovery current of the diode. That would then lengthen the total time at which we have large voltages across the switch and significant currents going through it. And the shaded area that I've shown here, right here, is indicative of the extra time that it takes, and that means extra energy being dissipated in the switch. We can eliminate that problem by using a snubber resistor in the position that I've indicated right here. That means during the time that the switch is turned on and the capacitor is discharging, all of that stored energy can be dissipated in the resistor and not in the switch. And the resulting waveforms then take on the form that I show here on the upper right hand side. The current in the switch builds up to the I0 value, continues to the peak reverse recovery current, and then drops down to the value in the on state of I naught. There isn't any further delay of the turn on interval as we had when RS is equal to 0. The current drops from IRR plus I naught to some intermediate value and then decays the rest of the way back to I naught. And that is with a finite value of R sub S. And the voltage fall time then is kept significantly shorter. It's not extended over the range that I indicated earlier over here, from here to here, because of the extra energy being discharged into the switch. The effect of the turn-off snubber can be shown in the graph that I'm showing here. In terms of the switching trajectory that I show here in the lower left-hand side, for small values of capacitance less than CS1, we improve the switching trajectory somewhat, but not significantly. When CS is equal to CS1, we are getting closer to the ideal switching trajectory. With larger values of C sub S, larger than CS1, the switching trajectory is further improved, but there's a price to be paid, as I had indicated earlier, by having an overly large value. That overly large value is indicated, the consequences are indicated here on the upper graph, where I'm plotting several normalized variables as a function of the capacitor ratio. The two important ones are the energy dissipated in the switch divided by a normalizing value that I call W base. W base is the energy stored in the capacitor, 1/2 V sub D times I naught times TFI. That's the charge that's put on the capacitor during that interval. As we increase the capacitor value, that energy that gets dissipated in the resistor is going to increase linearly as we increase the capacitor value. The energy dissipated in the switch, of course, goes down as you increase the capacitor. And the total energy that is dissipated in the circuit, plus the snubber circuit, plus the switch, is indicated by this dotted line. The minimum power dissipation total is about a capacitor value of about 1/2, the normalizing value. But if we go to the full value, CS equal to CS1, the amount of energy that is dissipated in total is not much more than what the minimum value is. And so generally, for most purposes, we say that a turn-off snubber capacitance value is equal to CS, and the value of the resistor can be basically the V sub dd over I naught. Here is a more detailed look at a turn-off snubber design procedure. As I already indicated, we probably want to pick CS equal to CS1. As far as the selection of RS, we want to limit the capacitor current to be less than the reverse recovery current, and that's equal to V sub D over RS. Now normally a designer wants to pick the reverse recovery current to be significantly smaller than I naught. A factor of 1/5 of the I naught is a typical number that's picked, and so that would give you V sub D over RS is equal to 0.2 times I naught. This snubber recovery time is something that you have to take into account, because we have to allow time during the time that the switch is on. We have to allow the capacitor to reset itself back to 0 volts. So the next time we turn off, it's ready to perform as we've indicated already. Since the capacitor voltage is decaying exponentially as a function of time with a time constant RSCS, we might use what's the time it takes to go down to 1/10 the initial value of the voltage. That's about 2.3 time constants. So that means you want your switch to remain on for at least 2.3 time constants. The word BJT is used here because when I initially made these lecture notes, I was considering the switch to be a bipolar junction transistor. Going on, the next type of snubber I want to look at is an overvoltage snubber. The overvoltage snubber is composed of this circuit fragment that I am outlining here: overvoltage resistance, overvoltage diode, and overvoltage capacitor. And I'm doing this in the context again of a step-down converter where we have a certain amount of stray inductance, L sigma. The overvoltage snubber is going to limit the overvoltage due to that stray inductance across the switch as the switch is turning off. Here is a waveforms that we observe across the switch, and the voltage across the switch and the current through the switch as a function of time during turnoff. We assume the voltage rises linearly as a function of time. When it reaches the power supply voltage, V sub D, the freewheeling diode can then accept the load current, and so we then have a overvoltage because of the stray inductance and the dIdt value, and I'm going to just call it a constant K times V sub D. Since I'm assuming a linear ramp of the current down to 0 during the current fall time, we're going to have a constant overvoltage of kV sub D. And the overall voltage is V sub D plus kV sub D during this interval. The value of that overvoltage is going to be equal to L times dIdt. dIdt is the I naught over TFI. Or if you like, I could express the value of the stray inductance in terms of the parameters, including that unknown constant K. The operation of the overvoltage snubber is diagrammed on this slide. At t is equal to 0, we assume that the transient turnoff of the switch begins. At that time, the voltage across the switch begins to increase. During that time interval, until the switch voltage reaches V sub D, all of the current from the load is still going through the switch. When we reach the voltage V sub D, then the current in the switch begins to drop down, and during the time interval when that current is dropping down, that means the current in the inductor is becoming less, and the equivalent circuit during the time interval as the inductor current goes to 0 is this very simple series RC circuit. The overvoltage diode is shorted out in that situation, and we can derive that the voltage or the current as a function of time during the time period when it starts to decrease is basically I naught times cosine T over the square root of LC. After a quarter cycle of that natural resonant frequency, the overvoltage reaches a maximum value. The current is now 0 through the inductor, and from here on the current will stay 0. After this time of that I'm talking about right here, which is assumed to be much longer than the current fall time, we then have the equivalent circuit shown to the right, which is a series RLC circuit, and so it's a damped sinusoidal response. The overvoltage maximum is the value that I'm showing right here, which one can get by computing what the LdIdt is and adding to it V sub D. But this is the increase in voltage above V sub D. And clearly, one way of minimizing that voltage is to have a large overvoltage capacitor. The question is, how much or what size should that capacitor be? Well, that's going to be dependent on how small you want to keep the overvoltage delta V switch maximum. If we go to the next slide, we can get into these details. Typically, we might want to limit the overvoltage to 1/10 of VD, the power supply voltage, which means then that the equation that I'm showing right here on the first line is going to tell us something about what the overvoltage capacitor ought to be. That's the equation that I'm circling right here. We've already been written that the inductor value can be written in terms of kV sub d TFI over I naught, which means I can then solve the first equation that I circled and get the overvoltage capacitor value. The second term that I'm showing here, the 100K TFI I naught over V sub d, is obtained by putting in the value CS1 that we had defined earlier. That is TRI times the I naught divided by 2V sub d from the turn-on snubber, or the turn-off snubber results. The only reason for writing it this way is to point out to you just how much larger the overvoltage capacitor value has to be compared to the turn-off snubber. We would choose the overvoltage resistance so that the transient recovery is critically damped so that we don't get any ringing in that time interval after the inductor current goes to 0. Well, that means that the Q of the circuit has to be 1 or less, and if we write it that way, we get the result that I'm showing here. And if we substitute in the 0.1 V sub d over I naught into the Q is equal to 1 equation, this is the result that we get for our overvoltage resistor value. And then finally, we would have to check what the recovery time is. The recovery time is basically about 2.3 or twice that, 4.6 time constants. And so that would mean that we want to keep the choice of resistor from above. Would tell us that the recovery time is given by the result that I have down here, where it's 46 times whatever that K value turns out to be times the current rise time. Overvoltage numbers in general are not used unless it's critically important, mainly because of the very large value that you have to have for the overvoltage capacitor. If at all possible, you would want to operate your converter without the overvoltage snubber, and that would entail then just choosing a device that has a higher breakdown voltage and simultaneously designing the complete converter circuit so as to minimize stray inductance values. The next snubber I'm going to talk about is the turn-on snubber. The turn-on snubber is indicated here in this box. It's the inductor LS, the resistor R sub LS, and the diode D sub LS. And basically the way the turn-on snubber works is something that I talked about earlier, and that is when you are turning the device on, the current is going to have to go through the inductor LS because this diode won't allow it to take that path as you're turning the switch on. And that means on the switching trajectory you have an immediate decrease in the voltage across the switch because of that stray inductance. Without the snubber, particularly that inductor, you would have the full power supply voltage across the switch as you are turning the switch on. So if we put it into a circuit and analyze what's going on, we can figure out then what the values of LS and the resistor R sub LS have to be. Here I show two different situations in this slide. If we have a relatively small value of inductance, small meaning the inductor value is less than a normalizing quantity LS1, we will have a waveform in which, as the current is rising, the voltage immediately drops down to a value less than V sub d. And it remains at that value until the current rise time interval is over and the current drops down from I naught plus IRR down to its normal on-state value. The voltage drop that we engender is given by this. This is the drop that I'm talking about from here down to here. And as you expect, it's equal to L times di dt. Now, I guess I can't draw another arrow here, but that indicates the magnitude of that voltage drop. If we choose a large enough value of inductance, whose value is equal to LS1, then we can drop the voltage in principle from the power supply voltage V sub D down to almost zero. And that would then be this critical value that I'm showing right here. It will depend on the specifics of your situation, just how much you want to drop that voltage in order to protect the switch. But there's another function that this inductor can take on if you use overly large values of inductance, that is greater than LS1, and that is to reduce the rate of rise of the current. If the inductor is larger than LS1, then what is going to happen is your rate of rise of current is going to be dictated by di dt is equal to the power supply voltage divided by I naught. And so your rate of rise is slowed down and takes longer to reach the peak value. And then your on time is defined here, is given by this equation, and the larger the value of Ls, the longer this time is, and thus the slower the rate of rise. And this is a protection measure you may want to take in certain critical devices like GTOs, for example, where you have to limit the rate of rise. The turn-on snubber has a recovery interval at switch turn-off, and that's what the waveform here is showing. Here we have the switch turning off. The voltage across the switch now is rising. When it reaches the power supply voltage, the current in the switch then can drop precipitously down to zero, as the freewheeling diode can now conduct, and the energy that is stored in the inductor, and thus the voltage that's being generated, can decay exponentially down to the value of zero across the inductor, and that transition time is about 2.3 time constants given here, which means you want to make sure that the off time of the switch is greater than that time constant. And the value of the over voltage which you get because of the presence of that resistor can be governed by the size of the resistor, and you probably would want to make sure that that value is somewhat arbitrary, but you don't want it to be a significant fraction of the total voltage. You want to make sure that whatever that over voltage turns out to be is well below the breakdown voltage of the switch. There are obviously several design trade-offs in this turn-on snubber design. The larger the value of Ls is, the less energy dissipation in the switch at turn-on. And I've calculated here what that energy dissipation is as a function of the value of the inductor. And we could normalize that to a value W sub B, which is the energy stored in the inductor, when we have Ls equal to Ls1. If the inductor value is larger than Ls1, then the amount of energy dissipated in the switch is essentially going to be zero. However, the large value of Ls larger than Ls1 means more energy being dissipated in the resistor. However, large values of Ls are going to reduce the reverse recovery current because of the slower rate of change of the current. Usually these turn-on snubbers are not used unless it's extremely important that you do so, because the inductor has to be designed to carry the full load current, and that makes the inductor large and expensive, and so a turn-on snubber like this is not used very often if you can avoid it by other means. The selection of the resistor is a consideration of the fact that smaller values will reduce the overvoltage at turnoff, and if you limit the overvoltage to 1/10 V sub D, then your resistor value is given by the equation that I've just circled. Large values of RLS will shorten the minimum time that the switch has to remain off, but it's going to increase the overvoltage. Finally, I talked earlier at the beginning the fact that I do have a little bit of information about Thyristor snubber circuits. Basically, a Thyristor snubber is the equivalent of a diode snubber, and in fact all that one normally does is change some of the notation and language that you use the diode snubber to be more commensurate with the application when you have snubbers. And I'm showing it here for a three-phase circuit. Most of you probably will not be involved in the use of thyristors in high power circuits, and so your interest in thyristor snubbers is probably not very great, and so I'm not going to get into the details, but I've provided the lecture notes in case some of you are interested in pursuing this particular topic. Thank you for your attention.